Good morning, students. So in today's lecture these pneumatic systems will be discussed, but before discussing these pneumatic systems, in industrial applications both pneumatic systems and hydraulic systems are used in automation industry. So before starting this pneumatic system, it is pertinent to compare these pneumatic systems and hydraulic systems. So here hydraulic systems, by this word hydraulic systems we refer to oil hydraulics, hydraulic systems which uses this oil, and this oil is incompressible in nature, whereas in pneumatic systems generally air or gases are used, air and gases are used as the power transmitting medium. So air and gases are generally incompressible. These air and gases are compressible in nature, where this oil is incompressible. We will discuss this hydraulic system in detail later, but it is pertinent in this particular lecture to compare these pneumatic systems as well and hydraulic systems. Okay. So, number 2 difference is that this is number 1, that this transmitting medium, one is incompressible, another is compressible, and number 2 is that air lacks lubricating properties, air lacks lubricating property, whereas oil is also having lubricating property. So oil is used as a medium for power transmission as well as lubrication of all the components which are used in case of hydraulic systems. So number 3 is the normal operating pressure, the normal operating pressure in pneumatic systems is much lower comparative to the hydraulic systems. Okay. So number 4 is output powers of pneumatic systems are considerably less compared to the hydraulic systems. So number 5 is accuracy of pneumatic actuator is poor. Accuracy of pneumatic actuator is poor at low velocities, whereas accuracy of hydraulic actuators are very much higher than the pneumatic systems. So next comes number 6. Is in pneumatic systems, external leakage is permissible, to a certain extent, but in internal leakage must be avoided because the effective pressure difference is rather small. In hydraulic system, internal leakage is permissible in hydraulic systems, internal leakage is permissible. Okay. So number 7 is no return pipes are required, no return pipes are required in pneumatic systems when air is used, whereas they are always needed in case of hydraulic systems. So, number 8 is normal operating pressure, normal operating temperature for pneumatic systems is 5 degree to 5 degree centigrade to 60 degree centigrade. So, this particular range is generally acceptable for pneumatic system, and in case of hydraulic systems, this range is, and this normal operating temperature for hydraulic systems. Here I am repeating once again that hydraulic means in this particular context it is oil hydraulics only, not water hydraulics. Okay, so this hydraulic system, the operating temperature range is 20 degree centigrade to 70 degree centigrade, almost comparable. The advantage of pneumatic system is that pneumatic systems are fire and explosion proof. Fire and explosion proof, whereas hydraulic system are not, unless non-flammable liquid is used, non-flammable oil is used in case of hydraulic systems. So, now I will give detailed discussion on the principle by which this proportional controller, by which different controller can be designed by using both pneumatic systems and hydraulic systems. Pneumatic systems comes first. Okay. So, throughout the discussion I shall place emphasis on the principle of operation rather than on the details of operation of the actual mechanisms. Only principle will be discussed. So, this pneumatic systems actually will be discussed first. These characteristics of these pneumatic systems are again described with the concept of this resistance and capacitance. You can see from this particular figure, one is resistance R, another is capacitance C, similar to the liquid level systems. This P bar is the steady state pressure. This P bar is steady state pressure. Now, if you change this steady state value, if there is a small variation of Pi, then there will be small variation of input flow, then there is input pressure, then there will be small variation of output pressure. So, in this particular system, this flow of air, this particular vessel is being filled up. This is the pressure vessel. Generally, in pneumatic systems, different pressure vessels are connected through some pipes, and this inside the vessels, this air or gases are stored at a higher pressure. So, that pressure is used in case of that particular pressurized gas is used for opening and closing of different valves which are used in industrial automation. So, in this particular figure you can see that this airflow Q is going to the vessel. So, as a result of which this vessel pressure is increasing. So, now if these two pressure at this upstream and downstream are same, that means at the steady state P bar, then this airflow, net airflow will be 0. Now, if there is some differential pressure, that is if there exists some delta P which is equal to Pi minus Po, that is input pressure, small variation of input pressure minus small variation of output pressure. That means this pressure is here inside the vessel, this pressure is increased by Po, and here it is increased by Pi in the upstream side. This is the downstream, which is nothing but vessel, this is the upstream side. So, because of this delta P, this flow will happen through this orifice here. This orifice will give some resistance to the fluid flow, to the air flow. So, now if this pressure differential delta P will be increased, then if delta P is increased, then this flow rate Q will be also increased. So, this R, this resistance is change of this delta P pressure differential change of this delta P actually divided by this dq. So, this delta P, delta capital P means this P bar plus Pi minus P bar plus Po. So, here this will be cancelled out. So, it is ultimately Pi minus Po. So, we should write here this delta capital P. So, when delta capital P is increased, Q is also increased. So, this R is defined in this way, R is rate of change of delta P divided by delta Q. So, this is again analogous with this basic electrical circuit. For basic electrical circuits, R is what? V divided by I. So, I is the current flow, that is analogous to the air flow, and V is the potential difference, that is analogous to the pressure difference. So, now it is generally this R is obtained from experimental plot that is shown in this particular figure. So, from this experimental plot, this delta P is measured at different, if delta P is increased, then Q is also increased, you can see, but it is not essentially linear. So, this R is obtained at a particular operating point. Let us say this is the operating point. So, for this, if you consider this at the operating point, so in the immediate neighborhood of the operating point, the slope of this particular curve, that is this slope of this particular curve at the immediate neighborhood of the operating point, that is the resistance at this particular operating point. If this operating point is different, if you consider no, this is the operating point, then your slope will be changed. Okay. So, this slope will be changed. This slope is basically measurement of this resistance, that is this slope, this angle is this divided by this. So, that means delta P, d delta P divided by dq. So, by measuring this one, as you have seen in case of liquid level, level systems. So, this same concept is used here. So, next is this C, capacitance. So, now let us focus on this capacitance C. This capacitance C is defined in the same way, that is change in gas stored inside the vessel, inside the pressure vessel. So, this is the pressure vessel divided by change in gas pressure. So, that means this is equal to dm by dp. dm means v d rho by dp, rho is the density. So, it is in the same line again, it is analogous to the electrical systems and liquid level systems. So, let us now discuss this particular, let us now focus on the systems first, this particular pressure system. So, here this, in the context of this system, what is R? This resistance R equal to Pi, this is the delta P, Pi minus Po by Q, and this C equal to this one dm dp. That means the pressure change dp0, this pressure change dp0 times dpo. So, pressure change dpo times the capacitance C is equal to the gas added to the vessel. gas added to the vessel during dt seconds. So, small time dt second, this pressure change is dpo times C, that is the. So, let me come to this particular basic definition. Change in gas stored, change in gas pressure, that is dp0 times C equal to gas added to the vessel, that means change in the gas stored. So, from this expression you can write down the C dp0 dpo, C dpo, O stands for output, equal to Q gas added to the pressure vessel, that means Q is the gas flow rate multiplied by dt. So, C dpo dt equal to Q, Q means this Pi minus Po divided by R. So, that means RC dpo dt plus Po equal to Pi. Next take Laplace transforms on both sides. So, RCS P0s plus P0s. So, this RCS plus 1 POS equal to PIS. So, output by input considering 0 initial condition, that is nothing but Laplace transform for this particular system. It is 1 by RCS plus 1. Now, look at this particular RC term RC, that is having the dimension of time and it is termed as time constant for this system. It is having the dimension of time, you can check it. So, this is the basic of this pneumatic pressure systems. So, next I am going to discuss, coming to the next slide, is pneumatic nozzle flapper amplifiers. So, in this particular diagram you can notice that this air supply is given through this orifice. Now, if there is supply pressure is Ps, then after coming through this orifice there will be pressure drop, because orifice is putting some resistance. So, this less amount of flow will be coming to this side. So, there will be eventually a pressure drop at this downstream side of this orifice. So, and you can see this is the flapper, this is called nozzle flapper amplifiers. So, let me tell you the operating of this system. This flapper is positioned against the nozzle opening. See, this is the X, you can see this is the nozzle opening, this is the nozzle. So, this flapper is positioned against the nozzle opening, the nozzle back pressure PB, this is the nozzle back pressure. This is called nozzle back pressure. This is controlled by the nozzle flapper distance X. This X is the nozzle flapper distance. So, as the flapper approaches the nozzle, the opposition to the flow of air through the nozzle increases. That means, as X is reduced, X tends to 0, then this flapper will come to this side. So, this X will be reduced. So, that will put more restriction to this air flow. So, that will result in increase of this back pressure PB. If the nozzle is completely closed by the flapper, the nozzle back pressure PB becomes equal to this supply pressure. Okay. So, if the flapper is moved away from the nozzle, so that nozzle flapper distance is wide, then there is practically no restriction of flow, and the nozzle back pressure Pb takes on a minimum value that depends on the nozzle flapper device. So, look at this particular graph. This along this x axis, this is the nozzle flapper distance. This is called nozzle flapper distance. So, at this point this is wide open. So, when it is wide open, so this particular pressure Pb back pressure drops to the atmospheric pressure Pa. Pa stands for atmospheric pressure. So, there will be eventually no restrictions when this is wide open. Now, gradually you are giving some input here, you are just pressing a pedal here, it is actually attached to a pedal in the actual mechanism, you are pressing the pedal. So, that will decrease this distance x. So, as soon as x is coming to this side, so this back pressure is increasing. So, when this x is 0, this back pressure is equal to Ps, supply pressure. Now, you can see in the middle of this, this part is linear, this part is almost linear. So, this control action can happen in this particularly linear zone. In this particular zone, this control action can be achieved. That means, if you control this input accordingly or proportionately, this back pressure will change. So, this is how this nozzle flapper amplifier works. So, this is the principle on which nozzle flapper amplifier works. So, now this note that this point is pivoted at some certain points, but instead of pivoted in another design, it can be floated also. It can be placed on a particular bellows which can move in either side. So, that design is used for different types of controls. So, now this type of control, using this type of control, you note that this PS is coming, this PS is not exactly coming here, PS is becoming reduced here. So, actually you are not going to handle a large amount of pressure, but a small pressure is being handled. So, this should be connected in series with another component that is called pneumatic relays. So, this is the first stage amplification. So, now it is actually generally insufficient to handle large pressure which is used in automation industry. So, for handling large pressure, you have to use another component that is called pneumatic relay, which is used in series with this particular nozzle flapper amplifier. So, let me now discuss on this pneumatic relay in the next slide. Pneumatic relays. So, this is the schematic diagram of a pneumatic relay. This is bleed type pneumatic relay. So, I will explain this bleed type. First, let me explain this basic operating principle of this pneumatic relay. So, this is as the nozzle brake pressure Pb increased. So, this is, you can see that this is one diaphragm. This diaphragm is pushed downwards, and when it is pushing to downwards, it is pushed to downwards direction. This particular valve stem, this is the valve stem is connected with this diaphragm in the bottom side. So, when this diaphragm is pushed below, because this nozzle brake pressure Pb increased, so this particular valve element will block this opening, block this orifice, whereas this is wide open, and this air supply, this main pressure supply PS is connected through this particular zone, and it is connected to the pneumatic valve. So, PC, that means control pressure is coming to here and supply pressure is coming to here. This supply pressure line is fully open to control pressure which is going to pneumatic valve. So, in this case PC is almost equal to PS. Okay. Just considering a negligible loss through this orifice flow, this PC is almost equal to PS, but it is not exactly equal, it is little less than PS. But this PB is somewhat used as a pilot pressure. That means PB is you are using this control to this particular error signal you are giving to this in this earlier side, that is this pneumatic, see here you are pushing this to this direction, so that will increase this PB. This PB is coming to, it is not going to this control valve. Instead of control valve, it is going to the pneumatic relay. So that is pneumatic, this PB is going to this pneumatic relay. This pneumatic relay is able to handle large amount of pressure. Okay, so this is actually bleed type relay. Why this bleed type is coming here? See, in this particular construction, when there is some equilibrium state, if it is not fully opened, this PB, when PB is maximum, then it will be fully opened. Then this will block, completely block this orifice flow, completely block this orifice. This orifice, here is a connection between this atmospheric pressure, atmosphere, and this particular pressurized air. So in all the times, except when it is completely blocked, when this line is completely blocked, or this line is completely blocked, when PB is 0, this point will go to here. So this is completely blocked, but this is open, but this is blocked. So this air supply is blocked here. So except at these two extreme conditions, extreme positions, in all the positions, in all other positions, whether equilibrium will exist or not, even if equilibrium will exist, there will be continuous loss of pressurized air to the atmosphere. That is why it is called bleed type relay. So this is not desirable, that is loss of pressurized air, continuous loss of pressurized air to the atmosphere is not desirable. So in another design, this non-bleed type relay is shown here. This is the non-bleed type relay. Okay. So this is, you can see this nozzle back pressure is coming to here, and this type of corrugated structure, this pneumatic air supply is coming here, and this air is going to this pneumatic valve. So control pressure PC is achieved. So air is, supply air is going to the pneumatic valve without any loss of pressurized air, it is going to the pneumatic valve. So this is actually non-bleed type relay. See, this type of corrugated structure is required. This is the valve stem which completely blocked this particular opening. Okay. So another type is also there, that is reverse acting relays. In this reverse acting relay, the nozzle back pressure PB, when this nozzle back pressure PB increases, this diaphragm comes down, and this particular ball, this ball valve, this is actually ball valve. This ball valve completely close this. When it is coming down, it will gradually close this particular opening through which this supply pressure is coming. Air supply PS is connected. So it is gradually blocking this orifice flow. Therefore, this when this pressure is increased, this air supply is blocked, is gradually blocked. That means this PC is decreased, this control pressure is decreased. So it is actually reverse acting. Generally, this relays are used in the forward acting. That means when this back pressure is increased, that will increase the control pressure. But here, that opposite thing is happening, that when back pressure is increased, this control pressure is decreasing. Okay, so this is called reverse acting relay. So now I am going to discuss one pneumatic proportional controller. So there are two types of controller. One is force distance type, another is force balance type. So first in this particular lecture I am going to focus on force distance type. So this is actually force distance type. You can see for this particular figure, this is the orifice flow is here. This pressure, supply pressure is directly connected to the control valve. This is the control valve. Okay, this is the control valve. So this corresponding pressure is PC. Now as usual, this PC bar stands for steady state. All these bars stands for steady state value. and this small casing letters are the little perturbation. Now, here this supply pressure is not at your control, it is not going to be changed. So, see this is the orifice here. So, through this orifice flow this pressure is supply pressure is considerably reduced in this particular path. Okay. So, this PB is increased as soon as you are pressing the pedal here, that means you are giving actuating error signal. So, what I mean to say here that you are going to handle with a comparatively small pressure PB to control this sufficiently high pressure PS. Okay. So, that is called pilot operating action, that is called pilot operation. That means you are not going to touch this high pressure, you are going to control only this low pressure. PB is the comparatively low than the PS. So, this is called pilot operating condition. Okay, pilot operation. So, now this is actually capital casing letter stands for steady state as usual. This Z is the diaphragm displacement of diaphragm, and this Y is this is the bellows, this is called bellows. This is has a typical corrugated structure, which will offer some kind of stiffness. So, let us say this stiffness is Ks. So, Ks multiplied by this distance y into y, that is equal to this pressure here, that is your control pressure multiplied by this cross sectional area. So, this is this point which I have already shown earlier, that see this is your error signal. This part is shown earlier that it is placed on a fixed fulcrum, this is on a fixed point, but it is in this case it is placed on a floating point. So, this is called the floating point. That means this can move in either side, whereas this is rigidly fixed, this is actually pivoted. Okay. Now, what is the importance of using this type of design? So, that I am going to explain now. So, see if you give some actuating error signal here E in this particular direction. So, this is actually connected with the pedal. Okay. So, if you press this pedal, so that will decrease this particular distance nozzle. So, this was originally capital X. Now, this actually this displacement, this arrowhead shown here, this is the positive direction of arrowhead. So, this is the positive direction of this X displacement of this flapper, this is the displacement of the nozzle, this is the positive direction. So, positive direction are shown by this arrowhead here. This is the positive direction of this bellows movement. Okay. So, as soon as this will be pushed, this PBU is increased. So, that will push this particular diaphragm downward. So, that will wide open this particular orifice. So, there is some flow of this pressurized air to this control valve, which is placed here. So, now this same control pressure is going to here also, this control pressure multiplied by A equal to Y. Okay. So, this Y equal to PC A by Ks. So, now look at this particular portion. Let us concentrate on this particular portion. Okay, in the next slide, see this is your feedback signal. So, here this feedback signal is coming in this bellows. Let us now consider on this particular zone. In the next slide, see here. Okay, so See, in this case, let me first explain with the help of this drawing. So, there is, this is the nozzle, this is the flapper I have drawn. So, if you give some actuating error signal here, so this will be positioned like this. So, this is your, this distance is B from this point to this midpoint, and this distance is A. So, that means this is your A and this is B. So, actually we are concerned with this distance from here to here. So, let us say this is your so this is actually how, what will be this distance? Let us say this is D here. So, D divided by E, using these similar triangles, D divided by E equal to this B divided by A plus B. That means D equal to B by A plus B into E. So, this is your B by A plus B into E. Okay. Similarly, if you consider now this is, I have told you that this is also linear system, linearized system. That means you are considering small variation of this x, z, pb, all the variables are considering or having small perturbation. Okay. So, that is this can be approximated as linear system, and in case of linear systems, principle of superposition is valid. So, according to principle of superposition, this is one case. In this case, we have considered that this point is fixed, this point is fixed, that is this one, but it is not actually fixed, it is actually placed on this feedback below. So, that means this point is floating. Okay. So, if you consider this floating, so in the next occasion you consider that this particular movement. So, for this particular movement, again I am drawing this flapper. So, this is actually original position. Now, due to this movement, this will be shifted to this side. So, this is let us say this is your y, small y, and this is again your b, and this is a. So, what is this distance now? In the similar fashion, this is your a by a plus b into y. So, if you apply now this superposition, principle of superposition, so this is the original flapper. Now, this is the signal E, and this is the signal Y. Now, notice that E should be greater than Y, E should be greater than Y, otherwise this distance, otherwise you will not get this distance. If E and Y are same, almost same, then this will be less, and if A and B are same and this E and Y are same, then there will be eventually no displacement of the flapper, nozzle flapper distance. Now, to obtain this finite displacement here, you require E should be greater than Y, that is feedback signal should be less than the actuating error signal. So, now this length is, if the method, if the principle of superposition hold is valid, then this length is equal to x equal to this b by, then this is valid because of this E, this is higher than this. So, this minus this. So, b by a plus b into E minus a by a plus b into y. So, this relation is important for further discussion. So, let us see here, and I have told you this earlier, this what is the relation between Ys and Ps. So, Pc, Ys and Pc, see here, okay, I have removed that one. So, Pc into A, this is your control pressure Pc and area is A. So, Pc into A equal to Ks, spring equivalent spring stiffness of the corrugated sheet, Pc into A equal to Ks into Y. Clear? So, now Ys equal to A by Ks into Pc. You take Laplace transform, Ys equal to A by Ks into Pcs. So, this relation is used here. Ys equal to Pc into, so we have derived earlier, Ys equal to A by Ks into Pcs. The Pcs is this one, this multiplied by A by Ks, so you are getting Ys. And in this particular summation block, you are getting this particular relation that we have derived just now, that is x equal to B by A plus B into E minus A by A plus B from here, this x, A by A plus B into Y. So, if you take Laplace transform, then B by A plus B into Es, this is positive terminal, minus A by A plus B into Y, negative terminal. So, you are satisfying this xs. Okay. So, now this relationship between Pc and xs, see from this circuit, from this particular circuit you can write this Pb, this back pressure Pb equal to this K1 into x, where K1 is the constant of proportionality, because I have told that this proportional control is acting in the linear region. So, it is actually linear relationship. So, K is the constant of proportionality, Pb is proportional to x. So, now this Pb is also proportional to Z, this Z. So, Pb is again equal to some other constant of proportionality multiplied by Z, and this Pc equal to this, if Z is increased, then also Pc is increased. So, this is also proportional. So, K3 into Z. So, that means this Z K3 into this Z can be Pb by K2, and Pb is replaced by K1x. Here Pb equal to K1x. So, this is equal to Kx, where K equal to K1 K3 by K2. Okay. So, Kx, that means Pc equal to Kx. So, Pc S equal to K into Xs. So, that is given here, Pc equal to K into Xs. So, this is the block diagram constructed for this pneumatic nozzle flapper amplifier. Now, this is the feedback signal. Y is the feedback signal. Okay. So, if you find out this transfer function Pcs by Es, then it is equal to A by A plus B into Es, A by A plus B into K see, this is actually negative feedback system. So, this is G by 1 plus GH. So, let us forget this. See, this is K divided by, this is your H and this is G. So, G by 1 plus GH. So, this is replaced by this single block here, and that is being multiplied by B by A plus B. So, that means this is B by A plus B, K by G equal to K by 1 plus GH, H means this into this. So, K A by A plus B into A by Ks. So, that means all are constant. So, this is your Kp. Now, although all are constant, you can vary this A and B by using a particular mechanisms which is not shown in this particular drawing, but in most commercial proportional controllers an adjusting knob or other mechanism is provided for varying the gain by adjusting this A and B. Okay. So, see this particular feedback mechanism, this Y, this is actually negating the effect of this actuating error signal. So, it is somewhat nullifying this actuating error signal. So, in that sense it is not very much sensitive. Okay. So, this actually this plus this equal to this. So, this is not quite sensitive compared to this fixed fulcrum flapper. So, that is the point to be mentioned here. So, see, it is actually this PS, there is, if this is fixed position, then it is sensitive, it is comparatively more sensitive, but you will not get the effect of this proportional control action, but it is actually to some extent more sensitive, because it is not placed on the floating point, it is rigidly fixed on the pivot. So, there is no feedback coming here that will nullify to some extent this actuating error signal. So, this as soon as x is changed, see, this is actually there is steep change, this PS to PA, there is steep change here, abrupt change, but in case of earlier design there was gradual change. Okay. So, it is called pneumatic two position controllers. Pneumatic two position means on or off, two position controller or on off controller. Okay. So, now I am going to discuss this basic principle for obtaining derivative control action. Okay. So, now the basic principle for generating a desired control action is to insert the inverse of the desired transfer function, is to insert the inverse of desired, insert the inverse of desired transfer function So, insert the desired transfer function. insert the inverse of desired transfer function into the feedback path. That means here. So, for this case, what is the closed loop transfer function? Cs by Rs equal to G by 1 plus Gh. Okay. Now, if Gh is very high, then you can see that Cs by Rs can be approximated as this one is negligible compared to Gh. So, this is approximated by 1 by H. Now, if proportional plus derivative, that means proportional plus derivative control is desired, then we can insert an element having the transfer function 1 by Ts plus 1 in the feedback path. Okay. That means here Ts plus 1, if this is actually 1 by Ts plus 1, that means equal to Ts plus 1. So, this is if this is multiplied with this input, then it is giving proportional plus derivative. So, this is derivative term, this is proportional term. So, that is the basic idea which we are going to use in the subsequent slides. So, look at this particular slide. So, this is already explained for pneumatic proportional controller. So, now we are applying this I have told you this 1 by Ts plus 1, 1 by Ts plus 1 means what? That is you have to put a restriction. You have already I have shown that, already I have discussed that in case of pressure system, this in case of pressure system that P0S by, okay, let me come to here. Here I was discussing the transfer function P0S, POS by PIS. This was derived earlier, 1 by RCS plus 1. So, RC is basically time constant. So, this is 1 by Ts plus 1. So, that means if you put one resistance here, this is for this resistance R. So, that means if you put this resistance here, this downstream transfer function by upstream transfer function, that is equal to 1 by, that is having this type of structure. So, here also you will use the same idea. So, in this case this pneumatic proportional. Now, here see the difference between these two. In this case this is direct, so it will lead to proportional controller. Now, if you put one restriction here, that is the R element, okay. So, that is done here. So, that will give you this pressure divided by this pressure, that is equal to 1 by RCS plus 1. So, that means here you can see. So, in this case see, this is your RC 1 by RCS plus 1, that means up to this it is okay. ES B by A plus B there is no change in this structure. A by A plus B A by Ks. Now here this is the PCS, this is the PC. So after the PC you are coming to this point. So between these two, this is the transfer function 1 by RCS plus 1. So here you are tapping this. So in the feedback path, this 1 by Ts plus 1, this type of transfer function is incorporated. So after this, it is connected as it is, as before. So only change is happening here. This PCS is forced to go through this particular resistance. Okay, so that will include this type of transfer function in the feedback path. Actually, this idea is that this pressurized, this control pressure, this PC, this particular air is slowly going to this capacitor C. So if you consider this actuating error signal versus this E versus time t, let us say this is the actuating error signal. You have pressed this particular pedal like this. So this control pressure PC, we plot this PC versus time. So that means this effect, this is the effect of addition of the restriction in the negative feedback path. This will modify this proportional control to proportional plus derivative control. Okay. So this is actually PC will be gradually and similarly this X also. Okay. So that means this feedback bellow, this is called the feedback bellow. This feedback bellow will feel the full effect of the actually this feedback bellow will not respond momentarily. As soon as you are giving this X, this feedback bellow will not respond momentarily, and the pneumatic actuating valve will feel the full effect of movement of, just I am going to make you understand physically that when you are giving this E, so at this particular moment this Y will not be affected, Y will be almost 0 because of this restriction. Okay. So this feedback bellow will not, because this feedback bellow will not respond momentarily, and the pneumatic valve will feel the full effect of the movement of the flapper. As time goes on, the feedback bellow will expand. The change in the nozzle flapper distance will be in this particular way. So this is the clear characteristics of the proportional plus derivative control action. Now considering this block diagram, what is the PCS by ES, B by A plus B into into K divided by 1 plus K A by A plus B into A by Ks into 1 by RCS plus 1. Generally this term is very high than this unity, so this can be neglected. So you will get this structure this is equal to Kp 1 plus Tds, where Td is the differential time and Kp is the proportional gain. Kp equal to Bks by Aa and Td equal to Rc. Td is the differential time constant. So, this is actually the basic principle of pneumatic proportional plus derivative controller. Next, this is pneumatic proportional plus integral controller. In this integral controller, this is this design is slightly different. This restriction is given here. Instead of here, it has come to this point. In case of derivative control, it was here. In this case, it is at this point. So, this bellow is separated by two chambers, 1 and 2. This capacitance, whole capacitance is C. Now, when this will be moved in this particular direction, so if you plot this error signal as before, error signal is this constant signal you are giving. So, what is the displacement of x now with respect to time? So, x will be started here. See, initially this part is restricted, fluid flowing through this part is restricted. Now, this part is open. See, this bellow is there is one link at the intermediate point of the bellow. So, that is connected to floating point. So, at this initially this will affect this feedback y. So, this y, it will feel the effect of this feedback y. So, due to this y, this x will be reduced, the x will be starting from here, let us say. So, as time goes on, this air flow will start, air will flow through this restrictor and it will apply force in the opposite direction. So, this will come to the opposite direction. So, it will gradually nullify this effect of y. So, that means this x, when it is gradually nullify this effect of y, this x will also increase. Similarly, this Pc, control pressure Pc will also follow this particular path. So, this is the characteristics of PI control. So, this in this case this PCS, so this block diagram, I think it is drawn here. Yes, block diagram is drawn here. In this case, this is the corresponding block diagram. See, this is the summing block. That means two signals are summed up here. Okay, let me do one thing. Let me copy this particular figure to here. Okay, now it is visible. So, look at this figure here. These two signals are basically, this part is okay. This is the summing block. Now, this is your positive feedback. This is your positive feedback part. So, let me explain this one. This PC is connected to here. One is this one, this A by Ks, this is as it is in case of proportional controller. So, this part is already explained. Now, come to this part. This part, this restrictor is put here. So, due to this restrictor, this is the corresponding transfer function. So, then that is multiplied by A by Ks, then this part is okay. So, this signal is going to add with this signal. So, this is the feedback signal. After this feedback signal, this was moving to this side. So, gradually it is again moving to this side. So, when it is moving to this side, this, look at this arrowhead of E. So, this is actually same arrow, same direction. So, that is why these two will be added. So, it is actually giving some positive feedback. So, now this is the next step. In the next step, this is actually simplified diagram of this. Up to this it is okay. Now, this is in this way, it is minus, this minus terminal is here, minus terminal is here. That means, this effect is, this particular position, this particular transfer function is same. So, that is why A by A plus B into A by Ks. Okay. Now, this is common to both this path. So, next you consider this minus and this plus. That means, this plus into minus, that is, it is going to negative terminal, and this minus into minus, that is why it is plus. So, these two effects can be combined by this particular structure. Now, this is in the next step, this is actually replaced by this signal into 1 minus, this is actually parallel connection. So, this whole thing will be replaced by this 1 minus 1 by RCS plus 1. So, this is your PCS by ES equal to A by B by A plus B into K divided by 1 plus K A by A plus B A by Ks into 1 minus, this is your 1 minus 1 by RCS plus 1. So, this is ultimately takes this form, this ultimately simplified 1 plus 1 by TIS. TI is the integral time constant. So, Kp is equal to proportional gain Bks divided by AA and Ti equal to Rc, time constant, integral time constant. So, next proportional, this is your Pi control, P proportional plus integral, Pi control. So, PD control was discussed earlier. So, if you combine this PD and Pi control action, then you will design, you will be able to find out PID control. So, this is the combination of these two. See, this restrictor is put on this path as well as on this path. Try to understand this difference. Here restrictor was put on this feed forward path. Here this restrictor is put on this feed forward as well as feed back path. So, it is leading to proportional plus integral plus derivative, that is PID control action. Okay. So, this is actually a combination of these two. Instead of 1, it is now RDCS plus 1. See, look at this, compare this 1 by RCS plus 1 in this case. In case of Pi, that is coming to negative port, whereas this was 1. Now, in this case, this will be Ri going to negative and Rd will go to positive terminal. See here, Ri goes to negative and Rd goes to positive terminal of this summing block. So, now this will give you the design of PID control action. So, similarly you can find out this PID, that means PC by PCS by ES. This is the output, this is the input. PCS by ES equal to BK by A plus B divided by 1 plus Ka by A plus B, A by Ks, okay, into RIC minus RDC S divided by, after simplification this will come RDCS plus 1, RICS plus 1 So, this is equal to, now as before, this 1 is negligible compared to this term. This is usually large value, mod of this is much greater than unity. So, ultimately it will be reduced to this structure Kp into 1 by 1 plus 1 by TIS plus TDS. Okay, where Kp equal to Bks by A and Ti equal to Ri C and Td equal to Rd C. Okay, so that is all for this pneumatic controller design. In the next class, this hydraulic controller will be discussed. So, thank you for your attention.